we will start with one aspect which I seem to have ignored, and we will do a brief interlude into what I call as mathematics of premixed flames. Why did I do this? In the 1970s, there are a lot of activity related to some mathematics of premixed flames, and what you will find in standard books of Williams and others who have led this business of the mathematics of premixed flames created a aura that everybody should do. Something also was done at institute. Show you the relationship to the simple expression that we have and also a certain question related to burning velocity. Burning velocity is often treated as an eigenvalue. Is everybody familiar with the idea of eigenvalue or no? Okay. If you take a spring mass system, you have something called a natural frequency. That natural frequency is an eigenvalue of that problem. You have the equations for vibration, then you can solve the problem, you will get somehow an equation in which you will find non-trivial solutions for specific values of a parameter. Those specific values turn out to be frequency. That is the eigenvalue. This eigenvalue is also there in matrix theory, you can calculate eigenvalues and so on. They are related to this aspect only. Okay. Flame speed or the burning velocity is an eigenvalue of the conservation equations. It is probably not well recognized because it is not taught these days in that mode. It therefore is important for us to recognize the meaning of it, just to elevate our elegance of understanding. It may not add much value to reality, but our appreciation of the physics will improve. So, what is it that is being said? You have a one dimensional flame of some thickness, at the center of it I will put a coordinate system, one dimensional, so only one coordinate x, and the conservation equations essentially related to heat balance as well as the mass balance, and U is written exactly like this: conduction, convection and reaction, with the H being the heat release. For the mass fraction of the fuel you can write the same thing, you can write it for oxidizer, you can write it for product, they are all related by stoichiometric ratio. In this particular analysis which I have chosen, there is a parameter called d rho Cp by k, which is called essentially Lewis number. I will show you the results for Lewis number equal to 1, which is pretty good for methane. For some other species like hydrogen it is different. It is not crucial matter for discussion here, but since the analysis was done like that, I will show you what it implies. What is shown here essentially is a set of transformations. Alpha is essentially the mass fraction at local location divided by mass fraction at unburnt state. Tau essentially dimensionless temperature, T minus Tu minus Tb minus Tu, Tb is adiabatic flame temperature. Some coordinate dy is equal to G rho u Cp by k into dx. Reaction rate term written like this, phi is some r by r bar, and here is one parameter called lambda. Lambda contains rho u square. This is in fact the parameter which is of importance. We define a quantity called p dt equal to dt dy. This is a mathematical transformation. We noticed that in this the coordinate goes from minus infinity to infinity. There is no specific location which has physical significance. I can locate it anywhere in this. In fact, that is in this spectrum of equations, that is the key to saying that flame speed is an eigenvalue, but you will not be able to see it in this mode. So, we make a transformation like p equal to d tau by dy is equal to dt dx essentially. Y is essentially related to x here and written like this. You will get an equation of this format: p d tau minus p equal to minus lambda phi tau. This is the diffusion term, this is the convection term, this is the reaction rate term. Corresponding terms for mass diffusion because of non-unity Lewis number, and the reaction rate expression. These are all at a time when things were being developed. Spalding wrote down, instead of E by RTB, he was more comfortable with an algebraic expression, but it makes no impact on the analysis. It was not probably not required. It was done. So, he took it like this and if you take Lewis number equal to 1, you can show in this equation very simple analysis tells you alpha plus tau is equal to 1. So, dimensionless temperature and mass fraction ratio they are all related to 1. Now, instead of showing here, I will go to the next slide where I put down these things because these are from the notes which I had used for classes in way back in 80s. For the case of normal diffusion, that means Lewis number equal to 1, that same equation will become very simply this. Alpha will become 1 minus tau, therefore, this is a function of only tau. There is no change, these two are connected. And n is equal to essentially you can show is proportional to E by RTB, and because activation energy is considered large for many fuel air fractions, it is a large activation parameter. This problem was discussed and solved by several researchers in the 1970s using what is called high activation energy asymptotics or singular perturbation theory, and this is different from regular perturbation. I will not go to describe what is singular perturbation theory and so on. I will just show you what it implies in a moment. Suppose you take a large activation energy, it turns out that the behavior of phi versus tau will be at nearly 0 everywhere excepting towards tau equal to 1. You see, as n increases, it goes like this. Reason is simple. For any tau, when n is very large, you know tau power n is very small. Half to the power of 10 is very small. So, you will discover that the phi is very small nearly everywhere excepting near tau equal to 1. This is also principle of activation energy asymptotics, where you say in a premixed flame, most reaction is concentrated at adiabatic condition, flame temperature condition. That is the classical approach. Suppose I take the right hand side as nearly 0 everywhere, we get P dP by d tau minus P equal to 0, for which the solution is essentially P equal to tau. What does this do? You see here P versus tau. P equal to tau it goes like this. You will see that it satisfies P equal to 0 at tau equal to 0, but it does not satisfy P equal to 0 at tau equal to 1, which is what is required in the P at tau equal to 1, P equal to 0. What is P? Essentially gradient of temperature. What this says is the gradient of temperature is 0 both at minus infinity and plus infinity, which is classical. There is nothing special about it. You do not find infinite temperatures, therefore, you must have gradients 0 at large distances. That is all the message. This shows actually it is going to infinity here, temperature is going to infinity here, it cannot happen. Now, that what asymptotic energy, asymptotic activation energy stuff will do is to bring this thing down to 0 at tau equal to 1, and this occurs because we have ignored the reaction rate term, and if you include it you will get it. But we do not go to a rigorous solution, but we will take a shortcut. If you integrate this equation from tau equal to 0 to 1 is nothing but 0 to 1 half of dP square by d tau, you just take it inside and you get this expression minus P integral B d tau is equal to minus lambda integral of 5 to 1. P is d tau by dy, it is equal to 0 both at tau equal to 0 and 1, this goes off, and you can write this simply as integral 0 to 1 P d tau by this expression. Now, P is equal to tau is true everywhere. An integral formalism, it does not matter if you ignore some, put P equal to tau, you will get essentially half. From this you get simply, I mean it is like stir something your gravy, just like that you will get rho USU is equal to this expression, which is identical to whatever we were discussing. Root of K by Cp into average reaction rate, this is nothing but average reaction rate expression balanced by the actual variation of reaction rate. So, the point I am making is, it's possible to do a rigorous analysis and justify that, but you cannot invalidate a simple analysis because it is obtained by a simple averaging process. This is the message I wanted to communicate through this. We discussed this canonical flames, canonical flames, and then we move to, we discuss this as well. So, we move to laminar diffusion flames. Diffusion flames occupy quite an important role in everything that is happening. So, we need to understand that. You can create it by using a jet or by something like an opposed jet flame here. In fact, my PhD thesis were roughly on this kind of problem, not relevant now, but it has significance of that kind. It has been enlarged into a very important tool for analysis subsequently by Peters, Williams and several other people. Now, you have oxidizer and fuel. Typically, if you take hydrocarbon kind of substances, perhaps something which has the same density as air, you take ethane, it is about same density as air, 28 and 29. Methane is not necessarily right example. If you want to do that, you could mix methane with nitrogen so that the density roughly matches. If density does not match, the flame cannot become flat like this, it will become curved because the momentum balance will not take place. Okay, that is a minor matter, but you have a flame here, and usually it occurs on the oxidizer side, not on the fuel side, because fuel air mixture ratio is large, 16, 17 for stoichiometry. You know, diffusion flame locates itself as stoichiometry, it is a principle. Now, so the fuel reaches through diffusion across this surface, oxidizer comes to it by convection, because larger amount of oxidizer is required to sustain the flame, that is all the logic. Okay. You then make measurements if you like, you will discover fuel and temperature peaks here, oxidizer is on this side, the temperature goes like this. This is the stoichiometric ratio, it is if you define this way, it goes to 0 everywhere else, it goes to infinity here. This is the zone where reaction occurs. This is the velocity which goes across like this, and the entire flame is located in this zone. You can make measurements of composition, which has been done. Oxygen falls down to very low values, okay. Methane falls down to low values, nitrogen is plotted here in some format here. You have CO, H2, CO2, all of them form in this domain. So, you will discover that the flame is centered around here. The diffusion of most radicals occurs to both the sides, okay. That is responsible for the initiation of ignition in some zones, okay. Yeah. You will also discover that if you plot it in this manner, you will find fuel drops down at the flame, oxidizer drops down from the other side, product goes up like this, peak temperature is obtained in this domain, like somewhat like this, okay. That is what laminar flame description is. Now, if you take a turbulent diffusion flame, make measurements, let us say in any one particular, at several zones you measure the temperature, local temperature and local fuel fraction, which you can measure, oxidizer fraction you can measure. By measuring the fuel fraction, you can see progress, how much fuel is consumed, converted, and that mixture fraction defined in a certain manner, subsequently it will be done, is a measure of how much is the progress of the reaction, okay. And you will see that as the mixture flow goes from 0 to 0.2, you will discover it moves from fuel to oxidizer or oxidizer to fuel, as the case may be. And you will see that measurement of temperature show a lot of dispersion here in a turbulent flame, okay. What this means is the flame is occasionally getting quenched and reignited on a continuous basis randomly. That is why you will find many data points here. If you take, for example, in this particular case, this shows you the measurement of the OH using laser induced fluorescence experiment measurements. Flame structure is like this, and flame is very thin. If you put a vortex here, you will see a breakup occurring here. All these are structures which are obtained in an actual flame. in a diffusion flame, and you measure the same thing in a strong flame, you will discover most of them are points are distributed around the expectation of temperature versus mixture fraction in the theoretical line, which is the black line. But if you see that is closer to extinction, you will find data points randomly located at many temperatures. What does this mean? See, in this case it means at 0.4 you would have to expect temperature of 2000 in a stoichiometry. But you will discover here at 0.4, in fact exactly at 0.38 or something like that, you will discover there are points at showing many temperatures. What it means is even in that condition there have been local extinctions and reignition. So, this is the property in an actual diffusion flame in turbulent influence of turbulence. Okay. So, this we discussed. I will skip this and allow Varun to speak about it some length. I want to move to droplet combustion behavior. You saw how it actually happens. I want to look at some features associated with it. We have a droplet in the flame around, and you will see this is the liquid vapor interface at RS, which is the droplet radius. The inner region, the temperature increases to the flame front and it goes down to the infinity. That is, this is the RS, RF and infinity, and this is the temperature profile. Flame can be treated as a thin sheet. Typical what happens? Reactions occur nowhere excepting at this sheet. Well, you can technically treat it as a Dirac delta function and analyze it. We will not necessarily do it here. The mass and heat flux balance at the surface of the thin flame, not thin flame, lead to the solution like this. M dot F is equal to 4 pi k Rs by Cp into log of 1 plus B, and B is called transfer number, normally called Spalding's transfer number, related to temperature ratios or enthalpy ratios. This expression leads directly to the d squared law, and in which the burn time is proportional to the droplet diameter squared divided by the burning constant. You will discover the flame radius also can be analyzed in terms of flame radius to droplet radius, and you can get this result. This analysis is pretty straightforward. Anybody can do it following the conservation equations. You can have it described in many books, and this burning constant is dependent on k by Cp into 1 by density, 8 by density and log of 1 plus B, again a standard result. What does this tell us? That if you take simply a 100 micron droplet, it will take about 5 to 10 milliseconds to burn. A 20 micron droplet will take approximately 200 to 400 microseconds to burn. As you bring down the droplet radius, the burn time decreases substantially depending on the surface area, and this is the key takeaway feature. That is why you must do droplet atomization is the logic. There is also experimental data with many fuels, N-octane, diesel, aviation, kerosene, all this meant for application related to air breathing engines. You will find this constant vary from 1 to 2, the burn rate constant. So, this is one feature which you can get from fundamental experiments, which will have value in what happens in actual systems. I just want to show you, you must have seen Stephen Turn's book, but if not seen, you will see it sometime. I happened to read it recently, for this course, otherwise I would not have read. Found something just strange, so I will bring to your attention those features. And in one page he says dimensional flame radius can be calculated from the same expression which I mentioned here, the same expression here, and you will get a result like 35. This is correct. What he says is the following: experimental values of dimensionless flame radius, which are actually measured, is about 10. They are smaller than what is calculated here. C.K. Law, very famous man, he written a book on combustion science, indicates that the fuel vapor accumulation effects account for this difference. It is not clear what is meant. This is his quotation from his book. In spite of the shortcomings of the theory, useful estimates of burning rates and droplet lifetimes can be obtained. Saying that you can get some features properly, but whether this is correct or not is a subject of question. This is something which bothered. There is a student of mine who called Professor Raghunandan, who is retired now. He did his work during his PhD time on this subject, because it bothered us. And the result is the following: that is nothing to do with all this. It has got to do with the fact that when you look at the property variation inside the flame in a coordinate system, eta s is the surface, eta equal to 1 is infinity, you will discover a behavior like this. You will find on the fuel side and the oxidizer side the specific heat, the thermal conductivity and the lambda by Cp vary through the field very significantly, and you can show that that integral of that variation is responsible for R by Rs. And the net result is shown in this table, where you treat lambda as constant, Cp as constant, you will get number of dF by ds 28.3, what he calls as 35, somewhere close to that. And you can take various approximations, but if you treat lambda as variable or Cp as variable, you will get this as 15. So, what is perceived as 35 is really, and then you draw conclusions from it, is patently wrong. That is actually 15 if you actually make a simple clear analysis using variable properties, is the message that I am telling you. But also there is one more message. You see this, all this is 1982 summary paper by C.K. Law, and look at our paper 1977. Now, this is something, is a message to you that you may do interesting work, but be please ready to it to be ignored in international literature. Now, if you ask me what does it matter, it does not matter a whole lot, but this is usually the order of the world. Which has been published in Combustion and Flame in 1977. It is not that Dr. C.K. Law does not know me or I do not know C.K. Law, we have met in conferences, spoken. And yet, you will discover they choose to ignore the work done in this country. That's the other message you should carry with you and be ready for that. Let us look at other influences on droplet combustion. There are forced convection effects in a dispersed environment. You know, every drop moves in a fluid flow field with velocity, and this is the statement which showed in a flow, and with flow the Reynolds number effect is taken into account. A small change will occur because of the flow. As droplet diameter comes down, the Reynolds number effect also comes down. So, in situations like, for example, in a gas turbine engine, I recollect Lefebvre, the famous man, gave a talk in GTRE long ago, maybe 76, 77, I do not quite remember, and he was posed this question from somebody from GTRE, what happens to the Reynolds number effect, and he gave a very correct and succinct answer. In the recirculation zone, velocities are very small, Reynolds number are very small. So, even if you ignore that effect, the errors that you create in the calculation of the flow field will not be significant. That is the correct message. It is not that you should not take into account the effect of Reynolds number in a code, you can take it, but if you want to understand the behavior, even if you choose to ignore that, the influence on the final result will not be very much, is the message that you get. So, that is one point which I thought you should know. Also, there are other features. It is not like a single droplet coming out, it is a spray, and ignition occurs occasionally in a group of droplets in a spray. So, there is something called group combustion dynamics, in which a lot of work has been done, and I do not think it has got a great influence on the code and the development of the combustion processes in gas turbine engines, but it is a science which you should be familiar with. Sometimes even to ignore something, you should know what it implies. And there are also effects of turbulence on fine droplet combustion behavior. Very fine droplets and turbulence interact with each other, and it is something that we should keep in mind. Again, there is the established body of literature, but I do not think the influence on the whole combustion behavior is very significant. So, in view of the complex flow behavior due to the above effects, and even if experimental data on burning constants under quiescent conditions are considered appropriate, validation and real combustion systems are required in view of variety of detailed models under development due to these complex effects. So, you cannot ignore them, you should factor them, but the validation comes only from a realistic comparison of performance, otherwise it would no longer be appropriate. I want to pose some subsidiary small questions at this time. Quite often it is said that some fuels are more easy to ignite, and so we say, why is it so? You will discover that the ignition temperature under the same set of conditions using different fuels, they turn out to be as though with carbon chain length. This is methane. As you go to larger end, you have N-heptane, octane, butane, etc., it will fall down. Bit strange, isn't it? You think that a simpler molecule should ignite it simply, but it is not true. Why is that? Methane has the highest ignition followed by higher octanes, and why so? See, larger molecules decompose more readily into reactive fragments than smaller ones, See, if the molecule is small, it requires greater energy to break it. Okay. For example, O2 is not as easy to break as CO2. You have ability, you have number of locations where collisions can become reactive and then break it. Hydrogen, the highest galactic molecule, is more difficult to auto-ignite compared to several liquid hydrocarbons. All these mean that chemistry matters with respect to ignition. Okay. These are matters related to chemistry. It is not entirely short duration, high energy inspired reaction chemistry either. The energy extraction process is due to flow including turbulence and a dynamic energy balance deeply influenced by chemistry, which will control the ignition process. Now, what I mean is sometimes ignition is treated as you hit a shock wave in a shock tube, you create a fuel source, you hit it with shock wave and determine the ignition delay and treat that as a measure of the ignition. That is different from you putting a gas into a flow field and determining whether you put in an ignition source, whether the flame will get sustained at ignition or simply the flame is blown off, which means it will not ignite. These are two different physical situations. Unless you take that into account, you will not be able to decide on the result very simply. Yeah.
In the previous slide, we discussed about the force convection effects on droplet interaction with ambient quiescent air.
Yeah.
In the earlier slides.
Yeah.
Yes. So when in droplet in the toroidal zone get entangled with the local flow field, then the local Reynolds number may be smaller, but the effect of convection on the droplet towards the droplet and the diffusion of the mass from the droplet will be having sufficient input on the flame interaction. But how we can ignore that?
No, nobody is saying ignore anything. No, I think you didn't understand the message correctly. I was addressing a situation in gas turbines. No, it is not. No, we will address every question, but you look at that question. There, you have air coming in a swirl mode, and you have spray. Spray means droplets until some zone, high density, and density comes down as you progress further. Some bit of evaporation, some bit of further atomization, secondary atomization will take place and you will get droplets. What is being said is the principal combustion occurs in a recirculation zone. The word recirculation means the flow velocities are small and also negative. That means the flow will actually turn around. Since velocities are small, Reynolds numbers are therefore going to be very small, and therefore the effect due to the convection will not be very significant in this situation. Now, if you take the case of liquid droplet, gaseous oxygen is flowing, liquid droplet, the flow there is quite complex and the atomization processes are not easy to describe. Okay? So, accepting that quite often you use a formula and pray that it works, there is not too much more that you can do. And the only way it works is if you have some kind of a model combustion chamber which is similar to the one that you are looking, you simulate the same set of conditions, you have measurements here of the progress of combustion, and that progress of combustion is actually compared with experiments with predictions. You will not be able to say with confidence that the model you have chosen is right. You may have gotten a correct result to a mix up of errors. It is possible, and it may be small, it may not matter. So, therefore, variety of such features occur in reality. Quite often you can ask a question, what is the use of the theory? So, it gives you a general direction of how to go about what may be happening, and using that you may be able to make a change in the design in some form or the other. So, I think one should not scoff at the fact of pursuit of theory, and one need not assume that every part of the theory should be very accurately represented. But we should be aware which part is important and therefore pay attention to it, not be guided by the fact that I have a theory which I have somewhere is written, so I am using it, it is correct because somebody has said it is correct. That all that argument may not work. Okay. So, I brought this to say that sometimes you will find this process of scaling of ignition does not necessarily mean also for combustion. And I am saying very specifically, burning velocity of premixed hydrogen air mixture is about 5 times more than straight chain hydrocarbons. So, just because it is difficult to ignite does not mean it so difficult to burn. There are different mechanisms at play, we must remember that too. So, different mechanisms are at play, early time dependent breakdown versus steady state back diffusion of reactant intermediates. There are two different features. Just please go ahead.
So, most of the times when we develop it, when we try to re-optimize our simplified kinetic mechanism, we use ignition delays and auto ignition characteristic as one of the two criteria for optimization of the rate parameters. But as is being mentioned here, what is being said is those parameters are like the kinetics which are being optimized by these parameters are not valid here, or what is meant by this?
Yeah, I mean to simply say that my kinetic parameters are optimized using auto ignition or ignition data, I want to use the same data for steady state propagation would not be correct. But you have steady state propagation information from premixed flames. Now, if it validates that, it is fine. It is possible in some regimes, that is in some stoichiometries, it may well be that the same kinetic mechanism is valid. So, I am not trying to say that there is a total invalidity between the mechanisms at play in ignition and propagation, but to assume that it is the same is wrong. To pay attention to in a given situation as to what happens in ignition, what happens in flame propagation. But if your aim is to simulate a propagating flame like behavior, you are better off in simulating propagating flames if it is premixed. If it is diffusion, you have to pay, you may not pay too much attention to chemistry if it is related to burning velocity, burning behavior. If it is related to emissions, you may have to pay attention to those aspects, and most usually it is turbulence interaction which matters. And when turbulence takes over, chemistry is brought down to that extent. Unless you are looking at specific aspects like NOx or CO, in which case the chemistry turbulence interaction is important, and considerable work has been done with respect to those species. Lot of effort has gone into modeling in turbulence chemistry interaction with respect to NOx generation, with respect to CO generation, and we have to look at those specific mechanisms, and some of the advanced codes actually use those methodologies which have been developed to varying degrees of success, and some of them have embedded in their codes the keep it in a protected form because they compare it with the experiments in their test beds. Comparisons look good, others should not capitalize on them, it is their property. On public domain you may not get that information, all these things will happen. Oh, I want to move to spray physics bit to understand a little bit more. This is a diesel engine, you will see the spray coming off from these injectors, and the spray physics involves and this diameter is about, I told you, 100 microns, 100 to 150 microns. It becomes droplets. The droplet atomization process is controlled by a number which is called Weber number, as you will see here, which is essentially the dynamic pressure of the liquid divided by surface tension driven force. It is a momentum ratio. So, if Weber number is large, the shattering due to aerodynamics is very significant. There are other mechanisms at play at lower speeds, but they are not quite relevant in the dynamics which occurs in engineering devices, where you want to push lot of mass flow into smaller domains, velocities are high, and therefore Weber numbers will turn out to be large. You will discover that many people have worked on this. In a diesel spray, for example, you will discover a correlation which tells you about the solder main diameter as a function, as a ratio of the diameter of the nozzle. This particular correlation tells you it is a maximum between two values, and two values are computed in some way, and all properties are described here about them. And measurements have shown that typically the numbers that you get is about 25 to 35 micron, and in some cases 10 to 20 micron. I am emphasizing this because of a general feature. You look at literature, you look at actual experiments, you will discover that the minimum solder main diameter obtained by best of the means of atomization take you to around 30 microns in gas turbine like situations, 10 microns like that in diesel like situations. In diesel injectors, you must remember the orifice sizes are extremely small, I told you, extremely small, and pressures are extremely high, and therefore they are able to get up to 10 to 20 micron. That is the number which I mentioned here. In gas turbine engines, the pressure drops are not that much. In some cases you use atomization because of air blast, it is even lower, and they want to use advanced methods of atomization, that is called high shear injectors. Even then the actual mean drop size you get close to about 30 micron. It is not easy to break it much beyond that, because the shear forces required to break it turn out to be very humongous. That is the only conclusion that can be drawn from that. Okay. So, this is from a work of a Japanese guy who has done a very careful analysis of the drop size distribution. In fact, current day engines, diesel engines, they hope to use ultra high pressure spray, and the reason why I want to bring it to your attention is, in these cases the velocities are so large that you actually get shock waves of the spray distribution, and that dynamics controls the atomization and of course combustion process. So, you will discover that modern day engines may really have more complex physics in the diesel engine, which is going to be developed over times. And typical combustion distribution you will see in each of the sprays. In approximately 1.5 milliseconds, the whole combustion is over, because it does not have much time in a periodic combustion process which occurs in a diesel engine. If you look at the spray characteristics relevant to gas turbine engines, you look at air blast atomizer, you have many parameters which control the atomization of something like kerosene, for example, and the pressure, as pressure increases, combustion chamber pressure increases, it inhibits atomization. As pressure drop increases, improves the atomization. That behavior is captured in this. And individual injectors, the flow rate is very small, 2.5 gram per second. There is something you should keep in mind. Even in a gas turbine engine, say CF6 or whatever, you will have about 20 orifices around, and each one pushes off something in the range of 2 to 3 gram per second, individual ones, at in an orifice of about 1.5 mm or half an mm to 1.5 mm size. That is the kind of orifice which you will get. Unlike in rocket engines, where the orifice sizes are much larger, 2.5 mm in 4 mm, something in that range. And if you take F1 engine, which actually used 5.5 millimeter, it is a very large diameter. Okay, there are various reasons for it, but the point to notice in a gas turbine engine, the numbers are not vastly different from what you see, and the number distribution of the drop sizes with fraction of the drops having a given drop diameter is shown here as a function of various parameters here. Pressure. You will discover that as the pressures increase, delta P increases, you will find atomization is much better, and as I told you, SMD will turn out to be in this case close to about 30 micron or so. So, you will discover that pressure drop across the injector is crucial parameter which controls the atomization. Rocket engines do not have that freedom, 10 atmospheres, 8 atmospheres, something in that range, not much more. In gas turbine engines, you can go to much larger numbers, you can go up to about 20, 30 atmospheres as well. In pressure atomization, in air blast atomizers, it will turn out to be much lower. And if you look at the spray, what matters also is how much the mass distributed over the spray, and that is shown here. You will see when the spray comes out at an angle, large amount of mass comes out in this domain, and combustion process is controlled by the availability of fuel in a specific zone. So, the flame structure is also will be such that you will find peak temperatures in these domains. So, I am summarizing it to say that the short turbine diameter in actuals is the actual spray volume to the spray surface area. Mean drop sizes are close to 30 micron, and this, as I told you, keep this general fact in mind. Drop size distribution describes the fractional volume in a small diameter range. The amount of liquid distribution across the phase shows that it is double peak matching with the influence of the swirl, and the combustion process is largely governed by droplet vaporization. Chemical kinetics of the combustion will be dominant only at the outer limits of high altitudes and moderate speeds. This also is important in gas turbines in steady combustion, not greatly important. For example, the way it reflects is that the combustion efficiency of a gas turbine at ground level operation will be close to about 97%, 95%, in that range. But the same engine, when works at high altitudes, 10 kilometers altitude, you will, and Mach number of 0.5, 0.75 or whatever, in that domain, the chamber pressures are lower, reaction rates are lower, and therefore they compete with diffusion rates, because you think the diffusion rates are low, reaction rates are fast. No, as pressure goes down, reaction rates are going down, therefore they compete with each other, and therefore there is an influence on it. They have discovered, for example, that the combustion efficiency goes down to 87% or 90%. They are unhappy, no, it must become 94. It is true, but that requires atomization, much better degree of atomization over the range, because you have no way by which you can change the reaction rates, that altitudes are fixed. So, these are the issues which we need to keep in mind. Okay, I told you that combustion chamber pressure in that zone will be lower. As I mentioned, Lefebvre has written a whole lot on this subject. There are a variety of gas turbine spray injectors designs which are described. It is not my aim to look at each one of them, just to point out to you that there are variety of designs. A more modern design is shown here, where you want to get, it is called high shear injector. It allows you to get a finer drop size distribution over a range of conditions, and Again, curiously, the book on atomization by Lefebvre and McDonnell provides information on the slaughter mean diameter. There are literally tens of correlations. I do not want to say hundreds of correlations, and the dependence on various parameters. You will see Weber number here, and another number called Onnes-Orge number, which is related to the viscosity and the surface tension being together here. All is presented here, but there are ever so many correlations. You will be left in distress. So, the only way you can do as a development engineer is perhaps to make measurements at specific conditions, look at the performance of the system and seek those set of numbers which are valid for yours. That is why many of these engine companies, engine houses that they are called, they have their own measurements, their own correlations. They do not tell you what they do. They allow Lefebvre, McDonnell to publish a whole range, but they do not say what they are using. A protected property, because they have put in effort to make those measurements and make sure that measurements are consistent with the experience on full scale engines. So, that is crucial. Okay. I bring out the fact that in these correlations, the dependence on Weber number itself is sometimes different, 0.6, 0.4 and so on and so forth. To depend on them bit dicey. So, one needs to put in effort and make calibration internally to make sure that results are consistent. This is the message you get from the study of these class of systems. There is one more way of atomization. This is another design of a combustion system used in an engine called Slinger combustor. One of the engines which GTR is developing has this class of designs. What does it do? Here there is a shaft in which there are holes. The shaft is run at the normal speed of gas turbine speed, in this case maybe 50,000 RPM or close to that. Because of the high speed, the liquid comes through this up to that point and gets sprayed by centrifugal action, and because the velocities are large, it is equal to that of spray, and then atomization occurs. And if you see here atomization at some speed, I have taken it from some other literature, you will see that as speed increases, the degree of atomization is substantive. And if you recognize that the engine which GTR is developing has an RPM close to 50,000, you can say that atomization must be reasonably good. And unless that happens, you will never be able to get good performance. This is another method of introduction of the fuel into a combustion system using essentially centrifugal action. Well, people have studied this behavior. Very interestingly, usually all correlations depend on the diameter of the injector hole. In reality, because of the centrifugal force, the liquid attaches itself to the surface which is moving forward, and so it forms a thin layer. It is not that all of the duct is really important in extracting the fluid, and so the correlations too take the slaughter mean diameter as a ratio of the thickness, which is obtained actually from an experiment itself, and they seem to show within the spectrum of noise a literally linear relationship with Weber number. With increase in Weber number, SMD goes down. That is all the message you get from here. Well, there is something to do with Onnes-Orge number, as I mentioned a little earlier. It has certain descriptive way the things behave. It has very little dependence on Onnes-Orge number, which is the ratio of the viscosity to surface tension forces. Okay. I think I have said what I need to say on many of the aspects. Some of them they are not coordinated in a sequential manner, but many aspects which contribute to the behavior, some commonalities and some differences is what I have described in this. Okay.